So that is Knut-Andreas Lie. He is a chief scientist at the Computational Geosciences group here at SINTEF Digital, and he is also the person who initiated the MATLAB Reservoir Simulation Toolbox many years ago. And he's here now to talk about and give us a quick overview of MRST and some of its most recent features. And with that, Knut-Andreas, I leave the floor to you.
Thank you, Øystein. First of all, if you notice that I'm looking up, it's not because I'm arrogant, it's just that my camera is mounted below my screen, so don't get put off by that. Okay, I will, as Øystein said, give an overview of the MRST. When we first planned this, we thought that we were going to talk much about advanced functionality, but then we noticed that there are many of you who are not that familiar or appear to be not that familiar with the software. So I'll start with kind of a general and a little bit gentle introduction that may bore those of you who know a lot about the software, but hopefully will help some of the rest. So the software, it started around 2006. We started developing what was first released in 2009. And since then, we've been having bi-yearly releases for a long time. So this is something that has been going on for quite a long time. What we think that the MATLAB Reservoir Simulation Toolbox is a unique prototyping platform that offers standard data formats that enables you to interact with the types of data that are used in industry. We offer data structure and library routines. One particular feature is that all grids are unstructured. This is for generality rather than performance. And over the years, we developed a number of tools that you can use in order to do rapid prototyping. And this is what the software is all about. It is primarily a research tool that enables you to test new ideas and work with models and so on. Yeah. Over the years, we have developed quite a large international user base. We have downloads from all over the world. The figure here shows Google Analytics. We use that for a period to track the access pattern to our web page. And this is the cities that we have downloads from in the period of July 1st, 2018 to December 31st, 2019. When you release a software like this, you don't really know what your user base is. Well, there are some people who write us emails with questions, but we really don't know what people use it for. So we started kind of collecting and tracking publications in which our software is used. And for this, we use Google Scholar, which whenever Google Scholar finds that somebody has cited the software, it sends an email and then we can collect it. So over the years, we've seen that there are 128 master theses, 64 PhD theses, 301 journal papers, and 155 proceedings papers that have been written by people outside our group. And we think that we try to put them up on the web page because we think that this is a good overview of the possibilities that you have by using the software. So if your paper is not on this list, please send me an email and I will put you there as soon as possible. So many people have over the years asked me why MATLAB and why not a compiled language. The main reason is that using a scripting tool like MATLAB gives you a different way of developing new ideas. You can use abstractions that express your ideas in a form that is much closer to the underlying mathematics than having to struggle with, for instance, for loops and things like that have been the tradition in older compiled languages. What I like most is that you can build your program using an interactive environment as you go. when I try to do something, I typically start with a kind of a small a script, and then I start running it, and I gradually build new functionality as I go. I try out how to implement things, put it into the script, go back and redo parts of it, and so on. And the reason why this is possible is that you have dynamic type checking that lets you prototype while you test an existing program. You can run it code by code lines line by line, inspect and change variables at any point. We'll come back to this later. People also ask about the efficiency of MATLAB. MATLAB is surprisingly efficient if you manage to use the correct way. So that is, you use vectorization, logical indexing, external iterative solvers, and so on. And we've put quite a lot of effort into doing this. So when you dive into the deeper details of the software, you may not always understand what's going on. And one of the reasons is that there are some cryptic constructs there that are in there in order to ensure computational performance. However, using a scripting language, you avoid the building project, which I always find to be a pain in the something. And you don't have to think of linking libraries and cross-platform problems and so on. Yeah, okay. So how is the software designed? Over the years, we try to modularize the software as much as possible. So we have a design where we have a small core that consists of mature and well-tested functionality, which we believe is used in many programs and different modules. And these modules, they are semi-independent entities of software that extend the core functionality and offer something that is a little bit specific. All modules must have code examples and/or tutorials that explain how they are to be used. And we also hope that most part of the software is documented in source, like in MATLAB. This organization into a core module and many independent or semi-independent add-on modules simplifies how we distinguish the public and in-house stuff that we have, and also the client-specific functionality. Because MRST is primarily a research tool that we have developed in order to support our own contract research, but we give the software away because we think that it benefits the work of others. So in the core module, you will find grid structures, grid factory routines, petrophysical data or data structures for petrophysical data. You will have basic fluid models, automatic differentiation library, and setting of boundary wells and source terms and so on that drive flow inside the reservoir. We also have a data structure that represents the state of the reservoir. There are visualization tools and so on. And then we have the add-on modules. In the latest release, there are 60 add-on modules, and there are more to come. I know of many modules that are in development, which we hope will appear in later versions of the software. Altogether, this last release consists of more than 3,500 files, 253,000 code lines, and 121,000 lines of comments. We also have more than 22,000 lines of C and C++ code, which is now much more compiled code than the MATLAB code we had in the first release in 2009. The software, unfortunately or fortunately, has two different programming paradigms. The older part that were developed primarily in order to study incompressible flow, consistent discretizations, and multiscale methods were implemented using imperative programming. And this is what we refer to as the incomp family of modules. These are functions that operate mainly on vectors, on sparse matrices, on structures, and on a few cell arrays. They use explicit assembly and linearization of flow equations. This proved to be quite good for a long time, but when we wanted to go into more complex flow physics, we saw that there were limitations. And for this, we started to develop what is today called the ADOO family of modules, which stands for Automatic Differentiation Object-Oriented. And this is a more recent addition to MRST. So in this setting, we have assembly and linearization is performed implicitly by the automatic differentiation routine. So the idea is that you code the equation, and then the automatic differentiation library differentiates and computes the Jacobians of a residual. We also have discrete operators and state functions that aid rapid prototyping. And lately, we've added memory-optimized backends and iterative solvers for improved performance. So that was the kind of the general introduction. Now I'll jump into telling a little bit how to get started with the software for those that are not very familiar with it. So first of all, there are two ways to get the software. The easiest is if you are a newcomer is to go to our webpage and then download the software by clicking the downloads software button here shown in orange. MRST is free under the GNU GPL version 3 license. It's released twice per year, and as Francesca said, the latest release was out yesterday. This release provides a self-contained file, archive file that contains all the necessary software. We also recommend that you subscribe to the MRST Announce Google group, which will tell you of new releases and, in rare cases, of necessary software patches in case there is something going on. We don't use this channel for advertising. So, once you downloaded your software, you can start by unzipping it to a folder. For this, you can use MATLAB. So assuming that we now have a file that's called MRST 2021b.zip, you unzip it using the command up here. And once the software is extracted to a directory, which typically will be something like home username and MRST 2021b on Linux, or something like this on Windows, you should move to that directory. And once you're in the directory, you run the startup file, and then you're ready to go. Alternatively, if you after having installed the software, when you restart the software and you stand in this directory, the startup routine will always be run automatically. Okay, so we are now ready to go. The startup script will present the following welcome message. And this welcome message presents you with several tools that are useful for getting to know the software. And I will go through them in some detail. The first one is the command that's called MRST example. So if you either run this in the prompt or click on it, you will get output that looks like this. So it essentially lists all the tutorial examples that are associated with the core module of the software. These are 14 at the moment, and I will later come back to the Flow Solver tutorial 1, which is kind of the whole hello world in MRST. The second on the list is the MRST path, which will list all the modules that the software is aware of. And here you will see that I have the AD black oil, which is located in a certain directory, and so on. This will be presented as a list in your MATLAB command window. And by making you can register, if you have additional modules, you can register to the path list, and then it will automatically be included into the software. So all these modules, in order to access their functionality, you should load them. And loading them essentially boils down to adding their directory where they reside onto MATLAB's search path. You can either do this manually by a command that's called MRST module add, or you can use the module GUI graphical user interface, which I show here, and then use the radio button to activate or deactivate individual modules. Of course, when you have such an extensive list of modules, you may want to know what the different modules do. And for this, we have a function that's called MRST Explore Modules. This gives you a window like this, where you on the left have a list of all the modules that are available. At the top, there's a brief description of each individual module. And then at the right, you have a list of the examples or tutorials examples that come as part of the module. And if you then move your cursor up and down the list, you will, in the middle window here, see a description of each individual example. The bottom window shows relevant literature with pointers to papers that either use this module or describe the module in more detail. And you can then view and extract the preprint or export the citation. The next thing we have is that the software comes with a lot of datasets that are included or that can be downloaded. And to view all of this, you can use the MRST Dataset GUI Explorer, which brings you up once again a list of the available datasets and a short description of each of them. In many cases, you can either push the download button to download the dataset, or the delete to delete it. You can be taken to a web page that gives more explanation. Once the dataset is installed, you can list the files, and you can see known examples that use these datasets. In some cases, the datasets are not available for direct download, and then the web page button here will bring you to the web page that gives you instructions how to download the dataset. Okay. In recent versions of MRST, we also included global settings that tell you a little bit of some automatic features that come with the software. That, for instance, allows you to download files automatically from the internet, whether you should be prompted before doing this or not, whether the software should automatically build next extensions for accelerated C routines, and so on. And also configure directories to store data and output generated by the software. Yeah, so that was all the information that you can get out of the startup message. Let's now move to the first tutorial. So the first tutorial is, as I said, kind of a hello world in simulation, where we compute a single phase gravity segregation. So the equation is like this, and what you see over here is all the code that's necessary to run and solve this single phase flow equation, and then plot and make the graph that you see over here. What you can see here is that this is the oldest part of MRST that uses procedural programming. We have structures, for instance, this rock perm for reservoir state. We have a structure G that contains the grid. We have a structure BC that contains the boundary condition, and so on and so on. The advantage of this is that we hide specific details of the geometry and the fluid model, which can then be passed around to different routines. The different functions are written with the vectorization to make efficient and compact code, and we kind of have a unified access to key parameters. So this is a good way to get introduced to the software. So how do you do this? Well, what I showed was an accept of the essential code lines. The actual tutorial comes equipped with a little bit more comments. It's been sectioned into comments it's been sectioned into sections that provide comments of what's happening. And the best way to look at the tutorial is to run it section by section. So when I get a new module or want to see a new routine, I always start by running the tutorials one section at a time, because this will give me a comment of what's happening, and usually there will also be some output that shows me intermediate results. And this you can do using the run and advance and the run section, or the advanced here up in the editor window in MATLAB. Alternatively, I often put a breakpoint at the first line of the tutorial. So that is, I move my mouse over here and click the horizontal lines next to the line numbers, and then I click run. Then I can use the step or step into or step out or run to cursor functions here to run the script step by step. By using step in, I can drill into individual functions. And this way I learn what is going on inside the software. Very often, or at least I'm often a little bit too quick, and I discover that I missed some detail, but then it's easy to go back and re-execute a statement or a script. And possibly if you, for instance, stepped past a function that you would like to look into, you then set the breakpoint inside that function and then re-execute it, and you can go into it. What I often also do is that I try to change parameters and re-execute and see what happens. And I recommend this as a good way to get to understand what's going on. At least this is what I've been doing for the more than 10 years that I worked with this software. If you want to learn more about the software, there are various things that you can use. First of all, we have the website. I must admit that over the years, it has grown in a kind of an organic way, and it's not as well structured and neat as I would like it to be, but it contains a lot of information. We also have the user forum where you can ask questions and hopefully get answered. We don't always answer all questions, and we generally encourage all of our international and national users to also help answering questions from other users. We have, or I have written a textbook called Introduction to Reservoir Simulation using GNU MATLAB or GNU Octave, which gives you an introduction to the basic parts of MRST. There will also be a forthcoming textbook any day now that's called Advanced Modeling with the MATLAB Reservoir Simulation Toolbox. And for those who spot the misprint in the front page of the book, I hope that this will be gone by the time it will be fully published. Then individual routines has man pages in the same as in MATLAB, and by saying help and then the name of a certain routine, you can go in and read about the different routines. We also, as I showed you, we have tutorial codes, and then we have a lot of or several online video tutorials that you can watch and get introduced to different aspects of the software. Yeah, so that was the introductory part. Let's move on to the feature highlights. The first thing I would like to say about recent features is that recently our capabilities of constructing advanced grids has increased quite a lot. So for a long time, we've been having Cartesian grids, rectilinear grids, corner point grids, tetrahedral, prismatic PB grids, and so on. And also the ability to do general polyhedral grids. But as you will see in 3 talks during this symposium, the first talk will follow by Runar Lie, who will talk about the UPR module for constrained Voronoi gridding. Then tomorrow, Lin Zhao will talk about the near well modeling module, which you see over here, that has been used to construct grid that adapt to well paths. And August Johansson will also, during the poster session, talk about using GMesh together with the MRST. We've also, over the past few years, spent quite some effort into making MRST have capabilities as in a commercial simulator. So we now have the ability to read industry standard input decks in the Eclipse format, parse this input decks, and create simulation structures that can be run as fully implicit simulators. So this will typically consist of a reservoir model that has grid, petrophysics, fluid behavior, and so on, and PVT behavior. Then we will have states that contain the standard variables, which for a black oil model would be the pressure, the saturations, compressibilities, dissolved gas or vaporized oil, and so on. And then we also have variables that represent the variables inside the wellbore. So that would be fluid rates, pressures, and so on. In addition, we will have what is called a schedule that describes how the reservoir is being controlled. So that is control policies for wells, and when these should switch, for instance, from being governed by bottom hole pressure to fluid rates, and so on. What you see to the right is a simulation of the full Norne field, which is a field from the Norwegian North Sea, where you see a comparison of what has been predicted by MRST and by a commercial software. And as you can see, there is an excellent match for this pretty complicated real-life setup. You may then ask, of course, what's the computational efficiency of a thing like MRST? Well, first of all, I would say that computational efficiency is not the only thing that matters. I would say that what matters is the total time of a program, which consists of the time that you spend programming, debugging, documenting, testing, and executing. So MRST is primarily designed to prioritize the first four of these. So that is the programming, the debugging, the documentation, and the testing. But of course, does this mean that MRST is slow and not scalable? Yes and no. I would say that to many will find that it's surprisingly efficient. There are, of course, potential concerns since MATLAB is an interpreted language, but the cure is that this just-in-time compilation that is used, vectorization, logical indexing, pre-allocation, and so on, that makes MATLAB quite efficient. There's also the possibility of having redundant computations, and for this we have introduced what is called state functions, which I will come back to shortly. That gives you a dependency graph and the computational cache, so that you don't do unnecessarily and redundant evaluations of all functions. There's also the computational overhead, which can be significant in MATLAB, and our cure for this is to use new backends for the automatic differentiation in particular, that uses memory optimized C++ routines to accelerate the derivation and assembly of linear systems. And for scalability and performance, we have recently extended our ability to use external high-end iterative solvers significantly. So the last two or the last three things here are discussed in great detail in the new book that will be forthcoming any day now. And I hope that many of you will read this and get to know more about these parts, which I find pretty exciting. So let's look at this a little bit in more detail. So what I show here is use of these new backends. So the graph shows along the x-axis the number of cells, and along the y-axis the assembly time in seconds for various operations. So the blue is the single-phase system, the red is a three-phase immiscible system, the yellow is a three-phase black oil system, whereas the purple one is a six-component compositional system. And as you can see here, when you have relatively few unknowns in your system, overhead dominates. But as you move to a larger number of cells, and this is now up to 2 million cells, you see that the scaling is almost linear, which is pretty optimal. So the takeaway message is that with small systems, you will have a significant overhead, but as you move into larger systems, this will decay and you will be able to benefit from high-performing iterative solvers, which tend to dominate the overall cost of your simulation. And just to show you an example, so this is a compressible three-phase black oil problem, which we solve with 8,000 cells, 125,000 cells, 420,000 cells, and 1 million cells. And here you can see that with the standard LU solver, you use 2.5 seconds with 8,000 cells. As you move to 125,000 cells, you soon hit the roof. You're using more than 500 seconds to solve the problem. However, if you go down to a compiled algebraic multigrid solver with the optimal preconditioning and a little bit of tweaks, you can make your solution time down to less than a second. And this scales pretty well. When you go up to more than 1 million cells, it increases by a factor according to the increase in the number of unknowns. And solving a three-phase black oil problem with 1 million cells in 3.8 seconds in MATLAB is not too bad, I would say. And all over, we then have performance that is not the same, but approaching commercial and compiled academic codes. And to give you another idea of this, this is the three-phase model with 1 million cells. And then you compare the time for assembly, which is the blue, the time per linear solve, which is the red, and the time to prepare the linear solver for 3 different backends. So the first here is the sparse kind of standard backend, which we don't do anything clever. In the diagonal backend, we try to optimize the memory structure by the fact that sometimes you're when differentiating a certain variable, you will get a diagonal Jacobian. And then we have last the diagonal backend where we use an optimal block structure. And as you can see, the linear solver time remains almost the same in all cases, but the time you use per assembly and also per preparing your linear solver drops dramatically. Okay, the next thing I would like to say is this thing about state functions. And what we would like to have is kind of dependency management. When you make a very complex simulator, you would somehow like to keep track of your dependency graph so that you know which derived variables that depend on each other and so on. Hopefully you would also like to have a lazy evaluation with caching so that quantities are not evaluated until you really need them. And you would like to have spatial dependencies in parameters while preserving vectorization potential, and you would like to implement independence of the choice of primary variables. So you would like to write your equations independent of which primary variables you use when you solve the system. For this, we have introduced a state function. So a state function is any function that is uniquely determined by the state structure that contains the reservoir state. So that would be the pressure, the saturations, component concentrations, and so on. And this is implemented as class objects in functional groups. So if you have, for instance, a state that contains 4 variables, a, b, x, and y, and you want to multiply x by y and then a by b and add the contents, this will be executed through state functions that do these operations. You will have one that extracts the data, one that multiplies 2 different data, and one that adds data and so on. The idea is now that to apply this concept to the whole simulation model. So that is, we apply it to evaluate flow properties for the PVT calculations, for the evaluation of accumulation, flux, and source terms, and also for the spatial and temporal discretizations. Altogether, this means that our simulator becomes a graph. And this graph can be differentiated, and now we're closing very much in on what's being done in modern machine learning, where you very often operate on differentiable graphs. So the figure here shows a state function diagram for a simple black oil model, where you have the states. So that would be the bottom hole pressure for the well, you have the solution gas ratio, you have the pressure, and you have the saturation. These all influence the PVT properties, they influence the accumulation terms, all the quantities that you compute in your well models, and the fluxes that go into the residual equations together with the accumulation terms. And here you see how they kind of all fit together. So arrows now means that, for instance, the viscosity depends on the pressure and so on. And each entity here is now a state function that is easy to replace. We also have introduced further granularity that enables you to code equations for immiscible components, black oil components, compositional components, and so on. And when combined all together, this means that you can combine at the runtime and make special purpose codes that only have, for instance, 5 components, that have 3 components, and so on, without having to operate with the general software that has n components and uses the memory of n components. Okay, for the last minutes, I will go through some of the functionality in some of the other modules in the software. First of all, I would like to draw your attention to the diagnostics module, which offers very interesting functionality for post-processing multiphase simulations. So here you see a multiphase simulation of the Bruges model, where we have clicked on an individual injector and then marked all the wells that are connected and asked to see all the wells that are connected to this injector. And there are a lot of tools there that enables you to find communication between wells in the reservoir, evaluate dynamic heterogeneity, and things like that. The diagnostics module also has a capability for pre-processing and ranking ensemble realizations without performing multiphase simulations. What you see here is a scatter plot of the Lorentz coefficient, which measures the kind of the dynamic heterogeneity in the reservoir. So that's the spread of the relative spread of the individual flow paths, the length of the individual flow paths versus their storage. And this Lorentz coefficient is plotted against the sweep efficiency after 1 pore volumes injected for the Norne model. And we can see here that the models that are likely to have high production efficiency will have high sweep efficiency and low dynamic heterogeneity, whereas modules that are not very efficiently produced will have high dynamic heterogeneity and low sweep efficiency. So here you see 4 different realizations, where over here you see proxies for the fluid recovery or the oil rate that you can observe over time. A new addition is also what is called the network models. And these are reduced order models that represent the reservoir as a set of one-dimensional flow paths that connect injectors and producers. So there will be a little bit talks about this later this week. Here you see these type of models that have been applied on the egg module, and we've used different ways of calibrating these modules. We've used the ensemble smoother on a full ensemble, or we also used the adjoint methods to calibrate the models. The last thing I would like to mention is the example suite, which is a new addition that gives you a generic interface to test cases. So the idea is that you write a simple function that sets up your test case in a standard form, and then you can call a function or a class that's called MRST example, and it will generate an example description. This example description can then be passed on to functions that plot the data, and it can also be passed on to the functionality we have for automatically running batch simulations, which is what is referred to get packed simulations. So all that is required to run and plot the results of one of these many data sets is to carry out the 6 statements that are here: setting up the example, plotting the data, simulating, setting up the simulation, running the simulation, getting the results of the simulation, and then plotting the results. And we already have a large number of examples that are available in this form. So that we won the Buckley level problems. We have the SB1, 3, 9, and 10 benchmarks. We have several Q5 spot simulations with 2-phase or compositional. We have the full Norne field, a simplified Norne field, and so on. Yeah, so I think I've used my time and a little bit more. So thank you very much for your attention. I hope that you learned something that has been of interest. If you have questions, please feel free to contact me in Zulip or write me an email or something. So at the end, I would like to thank all my co-developers, all our master and PhD students, and our national and international collaborators, and the funding that we have received over the years from the Research Council of Norway, from SINTEF, and a large number of industry companies. Thank you very much.